Okay, this is a problem where you need to deal with a piping system that supply water from the first floor to the second floor. So in this piping system, we have a inlet at point 1. Okay, and here we have a flow rate of water. Okay, basically this is your Q dot lah. Okay, and this water is actually entering to this pipe. Okay, it is actually a long pipe. This, but we want to simplify our problem. We start at this particular point, point 1. It is actually the diameter of the pipe is 4 centimeter. Okay, 4 centimeter, and it is a long pipe. But what we interested is that we want to measure, or we want to analyze from this particular point, point 1, and then the water is pumping or flow upwards, and it has a elbow here, 90-degree elbow at point 2, where the water is pushed upwards. Okay, push upwards at the height of 3 meter. 3 meter is roughly about 10 feet. Okay, it's about the height of a 1-story building. Okay, from the floor to the ceiling is about 10 feet lah. Okay, so the water is pumping up, and then you have another elbow here. Okay, and in this particular pipe, okay, the first pipe down here, from point 1 to point 2, you have a diameter of 4 centimeter. Okay, but then after this particular elbow, the size of this pipe is reduced to 3 centimeter. Okay, from 4 to 3 centimeter. Then you have another elbow, and then you have another pipe which is the same 3 centimeter. Then you meet this particular valve at point 4, and this particular valve is a type of ball valve. Okay, this is what we call a ball valve, B-A-L-V-E, ball valve. I think you can find this type of fitting or valve in many application, or even at your home. Okay, if you go to your the easiest one is you go to your gardening hose. I think you can find this, or alternatively you can go to your washing machine. Behind the washing machine you should have something like this as well. Okay, it depends on the type of valve that is used at your home, basically. Okay, but anyway, this valve is positioned at point 4 here. Okay, then after this valve, you have a smaller pipe which is only 2 centimeter diameter, and at point 5, what happens is that the flow is expand to atmosphere. So you will have a free jet at this point. Okay, that is what you are going to deal with. Remember, from point 1 to point 2, the length of the pipe is 5 meter. From point 2 to point 3 is going up at the height of 3 meter. And from point 3 to point 4, you have a length of 2 meter. Then from point 4 to point 5, you have a length of 1 meter. This is the system that you are going to analyze. Okay, and this particular pipe, this one, and all of the pipe is a type of a drawn copper pipe. It is a copper pipe which is stretched or drawn into a certain length. Okay, basically the type is this type of pipe. Okay, drawn copper pipe, because there are many of pipe that available, okay, in the market. Okay, the water is actually what we are dealing here is the water at the temperature of 20 degrees Celsius. Okay, we are not analyzing any sort of heat dissipation or heat addition. Okay, so we are not dealing with any heat transfer in this particular analysis. Okay, we assume that the temperature is remain the same from 0.1 up until 0.5. Okay, no heat loss or no heat is added to the pipe. Okay, so here we know that the Q is actually 1.5 liter per second, the flow rate of the water entering this pipe system, which is 1.5 liter per second. And you know that Q dot or flow rate is actually equal to area time velocity of the area of the pipe, and V is the velocity of the fluid at that particular point. Okay, let's say A is basically A is determined from this particular pipe, so therefore the velocity of the water or the fluid inside this particular pipe is this one, V. Okay. Okay. So this particular problem, what we are looking at is we want to see at the end of this analysis, what we want to really look is that we want to see how the pressure, okay, pressure characteristic or behave as it move from point 1 to point 2, from point 2 to point 3, point 3 to point 4, and point 4 to point 5. Okay, so from 1 meter, from 0 to 5, okay, from 0 to 5, and then from 5 to 5 plus 3, 3 is 8, right? So from 5 to 8, to 8, then from 8 to, you plus another 2 to 10, then the last one you add another one. So sorry, not in is it in feet? No, that is in meter. Okay, in meter. So from this is 0.1, this is 0.2, 0.3, 0.4, and it is at 0.5. Okay, so from 0 meter until 11 meter. So this is how it will behave, whether the pressure is going up or the pressure is going down. That is what we want to analyze here. Okay, by logic, is that make sense? Okay, common sense first, right? The energy principle first. Is that make sense that the pressure at 0.1 is lower than the pressure at 0.5? Is that possible? That is not possible. Okay. If the pressure here at 0.1 is lower than the pressure at 0.5, what happens is the water will flow reverse, backwards, will flow that way. Okay, it will come in from here and going down that way. If this is the case, okay, if this is the case, okay. Okay, and therefore, since we know that that is not possible, so we can safely say that the pressure at here is higher than the pressure at that point. So we can say that P1 is higher than P5. And therefore, most likely, the graph would be something like that. Okay, of course, there will be some hiccup somewhere here, or there will be some changes along this line. It will not be a straight line because of you are dealing with this. And then you have a different size of piping system. Then you have another one here. Then you deal with this. And then suddenly you expel the water freely. That makes some changes. Okay, so because of that, we need to do some analysis. Okay, so to actually see how it behave. So now I hope you understand the principles that as the water is flowing this way, basically what happens is that P1 would be higher than P2, and P2 is basically should be higher than P3, and P4 should be higher than P1, 2, 2, 3, oh sorry, P3 should be higher than P4, okay, should be higher than P4, and P5, sorry, I made a mistake. Okay, P2 is higher than P3. Okay, P3 is higher than P4, and P4 is higher than P5. This is the it should be like this. Okay, it should be like this. Otherwise, it doesn't make sense. Okay. Okay, now how to get into this graph? This is our final things that we want to have. Okay. Therefore, what we need to do is that we first analyze the velocity at each point. Velocity at point 1, at point 2, at point 3, point 4, and point 5. Okay, so how to do that? It's basically, since you know that the flow rate, okay, water flow rate is equal to AV, right? The water flow rate in this case should be the same and will be the same from this point up until this point, because there is no exit for the water to go out, or there is no other inlets that other source of water to coming in to this particular piping system. Okay, there is one inlet and one outlet, and therefore the flow rate of water should be the same at each point. Okay, only the difference is that the diameter as well as the velocity of this water inside this pipe. Okay, that's why we have this one. Q12 is equal to Q23 equal to Q34 and equal to Q45 at this end. Okay, they should be the same. But you need to remember that the pipe diameter is changing, right? So from 0.1 to 0.2 at certain diameter 4 cm, then from 0.2 to 0.3 as well as 0.3 to 0.4, the diameter is 3 centimeter. So this should be the same lah. And the last one, 0.4 to 0.5, there is a much smaller diameter, which is 2 centimeter, and therefore the area of that at that pipe or at that point is we denote it as A45. Okay. Then, as we know that the fluid or the water is at 20 degrees Celsius, and therefore you need to refer to this particular graph. This particular table. Okay, to look into the what is the density, what this is the density of that water, which is a 998, and also what is the viscosity, which is 1.002. This one, and it is the density, and it is the dynamic viscosity. Okay, here. And we also know that 1 meter cube is equal to 1000 liter, because we are given that the flow rate is in unit of liter. So that one you need to basically divide by 1000 lah. Okay. Therefore, you will get this value of in meter cube per second. Okay. As given here is that the area at each pipe is changing, right? Have a different diameter, and therefore you need to calculate the diameter of each of it. Okay, and this is the same because this one, it is the same, and this is the last one with 2 cm. Remember that to change the unit. Okay, for example, this one, that is a 4 cm, right? So therefore you need to divide by 100 lah, to convert that into meter. Okay, this part, don't forget. Many of you would just jump straight, use the whatever value without really looking at the units. That is wrong, absolutely wrong. Okay, now we will look into this after this. Now we want to calculate the velocity, as I just mentioned just now. Okay, the velocity at each pipe or at each point. So for the pipe 1, 2, we have the Q, right? Q12. Then A12, we have calculated just now. And now we want to determine this V12. So you rearrange this into this. Then just plug in all the values that you have. Therefore, you will get the velocity of the fluid at that particular pipe or at that particular point. Okay, and therefore, after knowing this velocity, you can straight away calculate the Reynolds number. Okay, rho VD over mu. All the constant is all the values is available. Then just put it in and you can calculate it. Similarly, you do for V at 0.23 and also its Reynolds number. Okay, you do the same process. Therefore, you will get this 2.1 meter per second. Okay, this is at 3 what call that one? 3 centimeter pipe diameter. And the Reynolds number is like this. Just change the V to 3 and also the D. Okay, from the previous calculation, just change this V and D value. And it is what you have. And as you know that the diameter of pipe 2, 3, and 3, 4 is the same. Okay, 2, 3, and 3, 4 is the same, and therefore the velocity as well as the Reynolds number should be the same. Okay, should be the same. And the last pipe, which is pipe 4, 5, it is how we calculate. Okay, it is the value of the Reynolds number. And then after calculating all this, you know the velocity, you know the Reynolds number, then what are we going to do? Okay, to proceed with the calculation of losses, okay, as we have gone through just now, we want to actually look into this sort of plot later on. So then what are the losses appear in this system? Okay, first of all, we want to consider the major losses that is due to the length of the pipe, of each pipe basically. Okay, you need to analyze each of it one by one. Okay, now we know that the diameter of the pipe is 4 cm, and then we have a 3 cm and 2 cm centimeter. And then we need to actually know what is the this particular value. Okay, I think it is called zeta over d. Okay, something like E, zeta over d, or roughness over the pipe diameter. You need to calculate this one. But before that, how do you want to know the value of this zeta or E? This is basically you need to refer to the type of the pipe. Here we have a drawn copper pipe. Okay, you need to refer to the book or to the table, something like this, one. Okay, so we know that we have a copper tubing, which is in millimeter, because we want to solve this in the SI unit. So in millimeter, it is given as 0.0015. Okay, with this particular value, okay, with that particular value 0.0015, you divide by 0.04 and you will get this value. Okay, and then 0.0015 0.04. Okay, I think I make some mistake here. It should be here, should be 0.0375. Okay, should be 0.0375. Okay, and I think this one as well, and this one as well. I hope it's just a typo error from myself. Okay, now after you calculate this one, you can use this particular equation to obtain the value of f. Okay, you can use this particular equation to obtain the value of f, or alternatively you can refer to this particular graph. Where was it? Yeah, you can refer to this particular graph. You already calculate the roughness, right? Then you already know what is the Reynolds number at that particular, for that particular pipe. Okay, then you basically refer to the for example, this is the value of relative roughness that you have calculated. Then you try to find the cross section. If let's say the Reynolds number is this, for example, so you just expand and should be there, right? So from here, take, go there. Then from here, you basically know what is the value of f. Okay, that is how it works. If you don't want to use that particular equation, okay, I more prefer to use this graph than that particular equation. Okay, this is more better lah. Okay, Moody, it is called a Moody chart. Okay, that particular equation is basically from here. Okay, Colebrook equation. Okay, if the flow is the Reynolds number is relatively low, which in laminar or transition state, you basically can use this particular equation. However, if you know that the Reynolds number is really high, then what happens is you can eliminate this. You don't need to actually account for that. You just do this. Okay. Okay. Okay, back to this one. Okay, basically we already obtained our F. I hope you can check on this because I have changed this value. Okay, it may change our calculation as well. But anyway, the concept should retain the same. Okay, then before we proceed further, for threaded elbow, because we are dealing with elbow, we have a valve as well as we have a outlet here that is free. Okay, then there will be some sort of losses, okay, minor losses due to the fitting. Fitting is a type of things lah, elbow, 45-degree slanting surface or something like that. So here for the threaded 90-degree elbow, it is 1.5, and for the ball valve, the loss coefficient, I would say loss coefficient 0.05, and the pipe exit, it is account for 1. Okay, it is for the minor losses later on, and this F here is very useful for you to calculate your major losses. This is the parameter that you need when you want to calculate for the major losses. And down here, it is the things that you are going to actually use when you want to calculate your minor losses. Okay, before we proceed with the calculation further, let note that you need to also calculate for the specific weight of the water in this case. Okay, because you might need to use this gamma later on. Okay. Okay, now we move to the first part of it, which is from the pipe is long, right? The pipe is something like that, and it is your 0.1, it is your 0.2. Okay, before, okay, that is the things. So basically here you want to analyze the pressure. Sorry, it's not going to be like that. Okay, I think okay. What we are going to do is that we want to calculate the pressure or the the pressure at this particular point, point 1. And then we want to calculate at point 2 and point 3, point 4. Point 5, you don't have to calculate because why? Because at point 5, it is open to atmosphere. So the flow is free to escape. And the pressure here is basically equal to the atmosphere. So we can say that the pressure here is equal to 0. Okay, at 0.5, pressure is 0 because it is open. Okay. Okay. So to make our life easier, we can calculate the pressure difference from 0.1 to 0.5. Okay. And later on, we calculate the pressure from 0.2 to 0.5 and 0.3 to 0.5 and 0.4 to 0.5. Why we do that? Because of we know the pressure at 0.5. Okay, we don't know the pressure at 0.1. We don't know the pressure at 0.2, 0.3, and 0.4. We don't know. But what we know is that the pressure at 0.5, and therefore we calculate the pressure at 0.1 based on the whatever information at this particular point. Okay, that is much more easier to do. Then, so we want to calculate this pressure 0.1 to 0.5. So what happens is that at 0.1, it is actually the whatever pressure or whatever losses appear inside the pipe. Okay, to make yourself much clearer, I did in 3 stages. The first one, the first part here, okay, this one, no losses. No losses. We got this value. No losses. Okay, we are not we didn't include the major losses or the minor losses. We didn't include that. Okay, on the second part, we do include the major losses. And on the third part here, we include the major and the minor losses. Okay, which one is the major losses? Which one is the minor losses? Okay, if you can clearly see, okay, from here to this one, it is repeated to this and this one. Okay, but for this one, we do include the major losses, right? And this is your major losses. And this is your major losses as well. Okay. And down here, we do include the both major plus minor, right? So this is your minor losses. Okay, clear? So you have without losses, then you add the losses due to the friction, have the F, friction, as well as this one, same thing, that is due to the major losses. Then you are dealing with the minor losses, K. Okay, if you refer back to this is the thing, K and the F. Okay. Okay, now, since we want to make our life easier, what we did is that we compare or we analyze from 0.1 and 0.5 because we know what is going on or what is the value of pressure at 0.5, which is 0. Okay, therefore we can start our calculation lah. where in this case, P5 plus, sorry, yeah, P5, whatever pressure that at point 1 basically is actually the addition or the added pressure due to the elevation. This is due to the elevation, okay, this pipe, and due to the velocity changes inside the pipe system. Okay, so this is the process lah. So at 0.5 it is 0 pressure. Then then you need to account due to the kinetic energy. Okay, this difference of velocity at 0.1 and at 0.5. Okay, that we have calculated earlier. So this part, and also the height changes. Height changes at 0.2, 0.2 to 0.3. If you refer to the earlier, if you refer to that diagram earlier, piping system diagram, okay, which is the elevation is 3 meters. Okay, so this is what we have calculated so far. Now, moving on, since we want to, the next part, we want to see what happens if we add the major losses due to the friction. Okay, due to the friction. To do that, okay, this part is still the same, still the same as what we have here. Still the same, but this part, this component is actually starting from here. Starting from here until here. Okay, these major losses. Okay, what we have is rho. Okay, since rho for this particular problem is the same, therefore I move it here. Okay, like so. I move it outside. Then we just deal with what we have here. We have F, we have the length of that particular pipe, L, and the diameter of that particular pipe, and the velocity at that pipe. Okay, square. So the first one, F1, is basically the value of this one. Because the pipe that we are dealing is the pipe 1, 2. The first pipe, right? Pipe 1, 2. Okay, pipe 1, 2. Diameter is 4 centimeter and the length is 5 meter. Okay, that is the thing that you need to remember. And therefore, you know, the length is 5 meter, right? So the length for the is 5 meter. Length is 5 meter and the diameter is 4 centimeter. Okay, L over D. F is you take from that particular table, this one. Okay. So that is the value of F. And 1.2 is actually the velocity that you have calculated earlier, which is this one, V12, 1.2 meter per second. Okay, you just plug in this particular value. And then done with pipe number 1, from point 1 to point 2. Then moving on to the point 2 to point 3, right? This is from point 2 to point 3. And also from point 3 to point 4. If you look here, there are 2 items, right? Because of, you know that the first one, the first part is from point 2 to point 3 is 3 meter. And from point 3 to point 4, it is a 2 meter. Okay, 3 and 2 meter. So this is what we have, 3 plus 2. Okay, divide by 3 centimeter diameter, or 0.03 meter. Okay, and then you multiply by the velocity. Okay, this part and this part is the same. Okay, you divide by the you multiply by the v square, the velocity at that particular pipe lah. Okay, and the last one also the same process. The value of f, the length of the pipe, as well as the diameter down here, and this is the velocity at that inside that pipe. Okay, you do the math, then you will arrive to this value. Okay, and for the next process, okay, I think I don't have to repeat this part here because it should be the same as what we have discussed up here. We only interested on the minor losses. Okay, okay. If you add both the major and minor losses, okay, the minor losses is this part down here, where you have your rho. I put it outside, similar to what I did up here. Okay, because of it is a constant anyway, so you only left with the KL, okay, the loss coefficient, as well as the velocity at that particular pipe. Okay, you have how many section? 1 section, 2 section, 3 section, and the fourth last one, 4 section of pipe, right? Not section, fitting. 1 at point 2, and then at point 3, at point 4, and the last one at point 5. You have 1, 2 item, 3 item, and 4 item that you need to deal with. Okay, and therefore you basically need to calculate each of it. Okay, this is due to the elbow, the first elbow. Okay, and this is the second elbow. Remember that the velocity is different because of the diameter of that particular pipe is changing. Okay, and then you are dealing with that ball valve. Okay, this is the value for ball valve. And the last one, because it is open to ambient or open to the water is move freely. Okay, so this is the last part of it. Okay, you calculate everything. This is what you will get. Okay, now basically, okay, if you want to actually draw this particular graph, you already have one particular point. You already have one point. Okay, somewhere up here lah. You only one point. So to plot a graph, you need a more than one point. Okay, probably 4 or 5. Okay, I think a minimum of 5 points to make it more presentable lah. Okay, so now you are done with this. Basically, without losses, if you ignore the losses, the pressure is about 40 kilopascal. Then if you only consider the minor losses, then the pressure is increased because you are dealing with losses, right? So that the pressure must be higher to overcome that losses. Therefore, you are going to get something like 50 kilopascal. Then furthermore, if you also would like to include the minor losses, then the pressure increase further, close to 70 kilopascal or 67.92. Okay, so that is the pressure that you have at this location number 1. Can you hear my voice? Hello?
Yes, doctor.
Okay. So so far, I think I have explained to you what is going on at the location 1. Okay. Location 1 is this one. Now we move to the location number 2. Okay. Okay. Location number 1 is done. So move to the location number 2. So location number 2, basically, we are dealing with P2. And again, to make our life easier, we compare to the pressure at 0.5. Okay. In this particular problem, you can either P1 equal to P2 equal to P1 minus blah, 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 or plus blah, 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 blah. Okay. Because of, you know, the pressure at 0.1 already, right? But I think I want to make it much easier for you to follow. Then we refer to the pressure at 0.5 instead of 0.1. Okay, because if I refer to pressure at 0.1, there will be some sign changes. The pluses might change to the minus. And I need to actually explain more if I would like to go that direction. But therefore, to make your life easier and to make myself much easier, and I think it is best to refer to the pressure at 0.5 in this particular analysis. Okay, and the same process is follow. Okay, the same process is follow, where you are basically dealing with the elevation, right? The difference of velocity at 0.2, the velocity is still the same, 1.2, as we have what we have calculated so far. Then that is what we have. And then, okay, moving on, this is the without losses, okay, up here. And this part is with the major losses. We have the major losses, and down here we have a major plus the minor losses. Okay. So with the major losses, since we are talking about 0.2, okay, since we are dealing with 0.2, so there are things that we can omit. Okay, not can, that we should omit. We should exclude. Okay, we are dealing with 0.2. So whatever the first part, we have to eliminate. We don't have to include that. Okay, which is the first one is due to the friction for pipe number 1, which is the length of the first pipe is 5 meters, right? So you have this highlight pipe here is you take it out, basically. Okay, I didn't include in my calculation, but here I purposely put it to make it clear for you guys. Okay, that is for the major losses. Other calculations should remain the same. Okay, and this is the value that you will get. And moving on, for the major and minor losses, if you would like to include both of it, what happened is that apart from this, which is the same, this and this should be the same. Okay, the things that you need to also exclude is the first elbow. You can take it out, the losses due to that elbow, because at 0.2, what we assume here is that in our analysis, 0.2 is basically just after the elbow. Okay, after the bending, so that the losses due to that 90-degree elbow we exclude. Okay, then it is the value that you will get. Okay, now you know the at 0.1 we have calculated earlier, and now we're moving on to the location number 2 or point number 2, that with the major losses, there is the changes, right? The changes is that okay, without losses, it should be the same, okay, because we didn't include the fitting or the other things. Okay, with major losses, we include the friction, right? So the value is different. You see that, as I mentioned earlier, P1 should be greater than P2. So by looking at this, it shows that your calculation is correct. Similarly, if you add the major and minor losses, okay, the pressure at point 2 is lower than pressure at point 1. So it makes sense, right? When you do any analysis, you must have that particular sense. Okay, it is not a sixth sense. It's just a basic principle of how things work. Okay, the basic principle of the pressure, how it works. Okay, now the same process you need to repeat for point 3. Okay, for the point 3. Point 3 is basically up here. Okay, point 3 is somewhere here, right? So now at point 3, you must remember that you are going to compare at point 3 and point 5, right? Just now you compare point 1 with point 5, the pressure, and then point 2, point 5, where you are dealing with 3-meter elevation. But now you are comparing point 3 with point 5, which is on the same elevation. On the same elevation. Okay, on the same elevation. And where the Z3 and Z5 is the same value, 3 meter and 3 meter. So this part here, you can remove it. Okay, you can remove this part. And the same goes to this part, this, because 3 meter is, this is the same down here. That is the 3 meter is this length, this one, 3 meter length. Okay, we only deal with 2 meter because 0.3 to 0.4 pressure at that point. Okay, you remove this, as well as for the minor losses, you exclude the next bend at 0.3, 90-degree bend, 90-degree elbow, sorry, this elbow. It is the first elbow and the second elbow. So what you left is the valve and this 0.5. Okay. So you exclude the elbow number 1 and elbow number 2. You only left with the what you call that, valve, ball valve, and the exit point at 0.5. Okay, and you do the maths. Basically, this is the value that you will get. Please check the calculation. I may make mistake. Okay, I may wrongly press the calculator because I do it manually. Okay, so please check the calculation as well. Okay, that is human error lah. But what I want to really share today is the principle, the process, the steps, the approach on how to analyze this particular problem. That is the main point here. Okay, there is the things. And what you need to really look at this particular point is that since we have elevation changes, the pressure at point 3 should be lower than point 2 because we have elevation changes, and therefore even without any losses, the pressure must be different because we do have elevation changes. Remember rho GH, the H, or this, in this case I put it Z. This part is actually, this part normally we put a rho GH, right? Or in this case I put it as gamma Z. Z is actually the H. Gamma is rho G. That is the thing. The same item basically. I'm using the different annotation, different symbol. Okay. Then you repeat the same process for point 4. Okay, the last one. Repeat the same process for point 4. Okay, at point 4, the elevation is the same, so you omit this one, you remove this, as well as the basically you only left with the last bit of the, or the last section of the pipe, which is the last 1 meter, the last 1 meter, right? From point 4 to point 5, it is just a 1 meter length. Okay, this is what you left with. Okay, okay, this one, right? The same thing lah. And for the minor losses, basically you only left with the at the exit. Okay, at the exit. P4 is actually right after the valve. Okay, after the valve. Okay? You can put that assumption in your calculation to make it clear. So this is the value. And at 0.5, P5, you don't have to calculate because you already know that P5 is equal to 0. Right from the beginning of our analysis, we already know that P5 is equal to 0. Okay, so this is what you will get later on. Okay, location 1, location 2, location 3, location 4, and location number 5. Okay, this is your location number 1, location number 2, location number 3, location number 4, and it is location number 5. Okay, and if you didn't include the losses, this is what you will get. This blue color, this one. Okay. If you only consider the major losses, this is what you will get. Then, if you considering more, in which you also include the minor losses as well, then it is the pressure that you will obtain, which is much higher. Okay. Okay, this is a measure from 0.1 because the first part of the pipe is 5 meter length, and the next part of it is going up 3 meter, right? So the first part is until 5 meter, and then it's go up to 3 meter, and then move horizontally to the it connect to the valve, ball valve, 2 meter, and the last part of it is from the valve to the exit of that particular pipe, the 2 centimeter pipe, which is 11 meter lah, the total length. Total length is 11 meter, so it is here 11.0. Okay, that's all for today. I hope you will get something